So welcome folks, we are working on solving today nth order linear ODEs, and we'll be looking at something called the characteristic equation. So this is sort of our next step after having solved some first order ODEs of various types, but the one that we were able to solve completely was the first order linear ODE using the integrating factor technique. We now turn our attention to our nth order linear ODEs. So here I've restated a generic nth order linear IVP. So it's nth order. Why is that? Because the highest order derivative seen in the problem is n. It's linear because as far as each one of these terms goes, it's a coefficient function multiplied to some derivative of y, or some coefficient function multiplied to y, or some standalone coefficient function. So it's linear. And careful, that's in terms of y. And it's an initial value problem because we see that we have these, how many initial conditions? Well, we've got 1, 2, all the way up to n initial conditions. So careful, this is counted at 0. So we've got n initial conditions here. One thing to point out is that this is an initial value problem because each one of those independent variables is the same in each case. Otherwise, this wouldn't be an initial value problem. It'd be something called a boundary value problem, which we'll look at briefly in class next time. So this can look a little bit unwieldy, so let's just give us a little bit more of a concrete example. We might have the natural log of x, y double prime, plus the sine of x, y prime, plus 3y is equal to x squared. So this is an nth, this is in this case a second order linear ODE. Notice that when I say linear, I'm talking about linear in terms of y and y's derivatives. The sine of x, for instance, is not a linear function in terms of x, but the sine of x as a coefficient function multiplied to y prime, that is a linear term as far as y prime is concerned. So that's what makes this a linear ODE. And we would have to be an IVP, we'd have to have two initial conditions, such as y sub 1 is equal to 2, and then something about y prime. Now for this to be an initial value problem, this number also has to be 1, and I don't know, maybe this is -3. So now we've got a second order linear IVP. So these are the types of problems, either just solving the ODEs or solving the IVPs, that we're interested in tackling. And we will continue to develop, we'll kind of increase the complexity of our theory as we go along, but today we've got some very specific tasks to look at. The first one is, just like we said before with our first order ODEs, before you go looking for a needle in a haystack, the first thing you want to confirm is that there is indeed a needle in the haystack. So we have an extension to the existence uniqueness theorems that we presented for the first order ODE that was called Picard's theorem. This only applies, so while Picard's theorem applied to any first order ODE, this existence uniqueness theorem assumes that we are dealing with a linear nth order ODE. So be careful here. So suppose we have these coefficient functions, a0, a1, an, and g. These are the coefficient functions here. And then we've got, sometimes I'll call this the forcing function here. If all of these functions are continuous on some open interval I, and then we have to add here a sub n of x not equal to 0 for all x in I, then this given IVP has a unique solution for all x in I. Okay. That might seem a little bit gibberishy. Let's take a look at it. Okay. So what we're saying here is we're asking the question, under what conditions will this nth order linear IVP have a unique solution? And it turns out that all we need is that each one of these coefficient functions plus this function right here, which I'll sometimes call the forcing function, each one of these functions need to be continuous. And then this one right here, we add to it the extra stipulation that it not be 0 on the interval. Then for any initial value problem that contains, any interval for which that's true that contains our initial condition, we will have a unique solution. So let's go ahead and pause there, and we'll pick this idea up in the next video.